So my name is Chris Rolfe, and I'm a principal security consultant at Montesano Security in New York.
And I'm Jan Avnitsky, and I'm also a security consultant in Montesano, New York, and we're both on Twitter, and that's our emails. And you should be able to find a more recent version of our slides in a few weeks on montesano.com/research. So today we're going to be talking about just-in-time compilers, what they are, why they exist, what they do. We're going to take a fairly deep dive into Firefox's JIT compilers. There's two that are currently enabled. We're going to talk about the LLVM just-in-time, just-in-time component of the LLVM framework. We're going to talk about some bugs that they inherently introduce just by the sake of being there. We're going to talk about some exploitation primitives that are possible because they're being used. Then we're going to talk about ways to mitigate a lot of these exploitation primitives. And then we're just going to survey the current just-in-time compilers and discuss our tools, techniques, fuzzers, and stuff we found.
So language interpreters and JIT engines in particular are responsible for doing a number of different things. They're responsible for parsing high-level language syntax, generating intermediate representation, usually in the form of a bytecode. They're there to optimize bytecode and then to finally generate native code at runtime in the case of a JIT. And whether most users know it or not, JIT engines are pretty much everywhere today. If you use any of the most modern web browsers, which I'm sure most of you do, almost all of them contain a JIT engine. Some of them contain more than one JIT engine. Language interpreters are another place you'll find JIT engines. Certainly we're going to get into this in the case of MacRuby and Rubinius, where the JIT engine is used to speed up the execution of interpreted bytecode.
Yep. And also Java.NET and pretty much any managed code is going to use just-in-time compilers too. So this is a pretty traditional view of how software gets developed and shipped to users. You'd have the developer write some source, feed it through a compiler, and then ship that to the end users. And in this case, if the compiler has any bugs in it or falls down, it's not really a security vulnerability in the traditional sense. Since it's on the developer's machine, it's all controlled. And all they care about is that the native code gets shipped correctly. So there's really no security boundary between the developer or the attacker and the compiler, since the compiler is kind of very isolated from the stuff you're compiling. JIT engines sort of shift that boundary really much farther from the user. So now the entire compiler is running on the end user's machine, and any bug in the compiler itself can lead to exploitation. And a lot of the ways that the compiler works can also influence the process that the user is hosting, and that is also vulnerable to attack. And just to note, technically a JIT is just a very small part of the entire compiler, but we're going to be referring to everything that happens on the user side as the JIT. So the entire compiler, code emission, optimization, everything, we're going to refer to that as the JIT. And we're going to use JIT as a verb a lot too. So whenever we say JIT, we just mean code emission or writing code into memory at runtime. So JITs are more or less new. I mean, they've been around for quite a while, but compilers have been around even longer. So compilers started appearing like 50 or 60 years ago. So they have a very rich history and very long history. So their architecture's kind of complexity has been moving with their history. So they're not just small components; they're fairly huge pieces of software.
And with the browser performance wars, now they're on everyone's desktop, whereas before they were only in certain language implementations.
Yep, because before you could just interpreting it and running from the source was running from the representation of the source was fast enough, but now they're kind of moving everywhere. So here's a similar diagram from earlier with a little more detail filled in, since the kind of general components of a compiler is you have the lexer, which just breaks up tokens, brings up your input stream into tokens. That's fed into the parser, which creates an abstract syntax tree typically, which would be an in-memory representation of the source. So it's a lot easier to manipulate and reason about code when you can actually manipulate it. Some compilers will go straight from the grammar into the native code emitter. V8 is a good example of that. There's really not that many optimization passes, or there's really no intermediate representation of source. Everything just kind of goes from the parser straight into code emission, into native code emission. But generally, though, from the abstract syntax tree, you could optimize it a little bit, but most optimizations don't really happen at the AST level. You would generate an intermediate representation of your code. And intermediate representation is it's closer to instructions than it is to the original source, but there's a lot more type information from the original language. So you could think of it as a kind of a non-machine specific assembly language that has that's a lot more expressive and has a lot more information in it. Then after IR, you can feed that into the native code generator again and emit your code, but you can also take a detour and run a few optimization passes and further optimize the IR. And typically, the intermediate representation is in a format that kind of lends itself to optimization. Since a lot of it tends to be in SSA form, which is static single assignment form, which does not allow reassignment, and that makes optimization a lot easier.
And not every one of these components has to exist.
Yep.
In more complicated JIT engines, all of them exist, but in some cases, only one or two of them exist.
Yep. And then if you're talking about LLVM, where it's a library, a set of libraries, you can implement all of them, or you could just choose not to implement. You could choose not to optimize. But eventually, basically, you always have input as source or untrusted IR, and then the output is always native code.
So here's a more concrete example looking at Firefox. So, we're all familiar with JavaScript. Here you have a small JavaScript snippet. It says the variable A equals new array object. So the SpiderMonkey engine is going to parse this syntax, it's going to tokenize it, and it's going to create this SpiderMonkey bytecode instruction called JSOP new array. And that single SpiderMonkey bytecode instruction is responsible for calling all the C++ functions that are going to instantiate this new array, initialize it, set up all its methods, callbacks, and so on. And the JIT engine is going to take that single instruction and turn it into a bunch of much, much faster native code.
And generally, when we're going to be talking about intermediate representation and it getting converted to something closer to the machine, that's called lowering. So whenever there's an intermediate representation that gets turned into native code, it's referred to as lowering of that instruction set.
So we mentioned intermediate representation a few times now, and usually intermediate representation comes in the form of a bit code or a byte code, right? It's usually some sort of binary instruction format that's not quite machine level, but not quite source code level. So it maintains a lot of type information, and there's different types here, and we'll go into this in a few slides, but the bytecode can either be really expressive and bloated and kind of slow, like kind of in the case of SpiderMonkey. It was written at a time when putting a JIT engine in a browser really wasn't on anybody's mind. Or the bytecode can be really simple instructions that are more closer to a machine level type instruction. They don't have as much type information. And we also see this in another bytecode format that's found within Firefox we'll go into in a few minutes. And another thing to note here is that the bytecode, once an attacker has control of a process, that bytecode interpreter is entirely usable, right? It's a state machine in its own right, and you can tell it to do things instead of writing your own arbitrary shell code.
And semantically, bytecode and bitcode are the same thing, but like it's more of a implementation detail of how you store in disk and how you're reading it.
So bytecode or bitcode comes in two different formats in our mind. There's an untrusted bytecode, which we're defining as bytecode that comes from an external entity, such as someone over the internet you don't trust, right? So a good example of that would be Flash, for example. When you get a Flash movie or some Flash SWF file, there's a bunch of compiled action script. It's already been compiled down to its bytecode format. So this is completely external to the compiler. Some developer wrote some action script or wrote some high-level language, compiled it down to a bytecode, and then sent you the bytecode. We're considering that untrusted bytecode. And then, of course, there's trusted bytecode. And what trusted bytecode is we define trusted bytecode as an intermediate representation that's always produced by a trusted component, a component that you trust. And a great example of that is the SpiderMonkey JavaScript engine in Firefox. There's no way for an external web server anymore to feed SpiderMonkey bytecode to the SpiderMonkey engine over the internet. It just doesn't work that way. The only way to get inputs into the SpiderMonkey engine is through JavaScript, which it then generates an intermediate representation. It then generates its own SpiderMonkey bytecode instructions. So we consider that trusted. But again, even though this is a trusted bytecode, quote unquote trusted, it's still potentially usable to an attacker who's already taken over your Firefox process, right? He can still overwrite some intermediate bytecode representation in memory and then tell the interpreter to go and execute it.
And just another way to think about it is where that boundary gets drawn from our original diagram, whether the lexer and the parser and all that, that happens on the developer's machine or that happens on the user's machine.
So there's a number of different JIT designs, and two we focused on we're going to talk about here. And the first one is a tracing JIT design. And what a tracing JIT design is it watches and it records the execution of interpreted bytecodes. So a good example is you've watched a loop happen 5 or 6 times. Well, it's pretty reasonable to expect that the same loop is going to happen a 7th, 8th, 9th, and 10th time, and it's probably going to look very similar. It's going to use the same types. It's going to execute the same exact way. So a tracing JIT, in this case, would step in and turn that interpreted bytecode that's just executed 6 times into a bunch of native code instructions. And one of the benefits you get from a tracing JIT is the types are already known because you've already watched this bytecode execute a number of different times. So you can make a pretty good guess on, the 6th time it operated on integers, the 7th time it's probably also going to operate on an integer.
Yep. And this assumes that the performance gain you're going to get from emitting code is going to be greater than the amount of time it took to emit all that code.
So an example of a tracing JIT engine is TraceMonkey. TraceMonkey was the first JavaScript JIT engine introduced in Firefox and was introduced in version 3.5. And it is a tracing JIT. And TraceMonkey, what it does, it uses a recorder component, like I said, to watch the execution of interpreted bytecode. And it uses this backend component called NanoJIT, which it shares with the Tamarin and Flash project to sort of generate assembler code assemble native code on the fly. So the TraceMonkey, what it does is it uses this recorder component to watch the execution of SpiderMonkey bytecode. And I believe on the 8th iteration of execution of those blocks, TraceMonkey kicks in. And what it first does is it produces these trace trees for the various different types that this bytecode that's been executing might encounter. And those trace trees are then used to generate this other bytecode representation called LIR, which stands for low-level intermediate representation. And the LIR bytecode is a lot more low-level, it's a lot more slim, and it's used to produce more optimized native code. And that LIR is going to be fed to that back-end NanoJIT component that's shared with the Tamarin and Flash project. And NanoJIT is what produces native code out of that bytecode. And there's a problem with TraceMonkey is that it actually doesn't handle type changes that well. So for example, like I said, if you're operating through an iteration of loops and on the 5th loop it's an integer, but on this, the 6th and 7th loop it's a string, it has to use a different trace tree. And that requires going back through the interpreter and doing some operations to account for that. So there's a reason that Firefox implemented a second JIT engine, which I'll get to here in a minute. There's 2 really interesting classes in TraceMonkey that handle the allocation of JIT pages that are going to hold native code. The first one is the CodeAlloc class. And what the CodeAlloc class does is it calls low-level API calls on Windows and Linux. It calls virtualalloc on Win32, and it calls mmap on POSIX platforms. And it's going to allocate all its memory readable, writable, and executable. And then the second class, the more interesting one, is the CodeList class. And what the CodeList class does is it has a bunch of metadata in the JIT page itself. So it stores a next, a terminator, and a lower pointer on the first part of the JIT page. And that's used to create a doubly linked list of JIT pages in memory. And if you're familiar with heap overflows from about 7 or 8 years ago, you can easily overwrite these pointers to gain arbitrary 4-byte writes anywhere you want in memory. And the problem here is that they made the same mistake that glibc made in 2002, which is there's no consistency, there's no checking on those links. There's no checking that they actually point to one another. And again, another bad part about this is that this data is stored at a static offset from the beginning of every JIT page. So if you want to overwrite one of these pointers, you simply just allocate lots and lots of JIT pages, and then you just pick one at random that you hope is in the space you've allocated, and you write the 20th byte from the beginning of the page, and you've overwritten the next pointer.
Cool. So tracing JITs really make sure that they're not doing any extra work and they're only kind of emitting code that's only hot code. Method JITs take a slightly different approach. Instead of having all that framework that kind of watches code and traces and makes sure that you're only emitting performant code, method JITs just take a block of code that represents a function or a method and just emit it wholesale. And this kind of removes the necessity of tracing and reasoning about code. And if your emitters performant enough, it might make a lot of sense to just emit code always. And I believe dynamic language runtimes take this approach for the most part, with some exceptions, which we'll get to in a little bit.
So I said before, Firefox has a JIT engine called TraceMonkey. They also have a second JIT engine called JagerMonkey. And this is a brand new JIT engine. It was just introduced in Firefox 4.0 just a couple of months ago, and it's a method JIT. And Firefox has borrowed the Nitro assembler from the WebKit project, as it's analogous to the NatoJIT engine in TraceMonkey. And what it does is it takes the SpiderMonkey bytecode and it produces native code during runtime. And one of the really cool features about JagerMonkey is its inline cache. And what an inline cache is the ability to handle different types and dynamically typed languages on the fly. So JavaScript's a dynamically typed language. So we have this example JavaScript function here, function blah. And what function blah does is it just goes through this for loop, and it calls this plus equal operators on whatever that argument that was sent to that JavaScript function is. Well, the hard part is, how do you JIT this function properly? Because B can be a number of different types. It can be a string, it can be an integer, it can be a regular expression, it can be anything in JavaScript. And that operator will still work on it. So the way that JagerMonkey and JIT engines with inline caches handle this is they say, every time a type is sent to me, every time an argument is sent to me, I'll check its type. And if I don't already support that type, I'm going to go back through the interpreter, look up its type, and then I'm going to dynamically generate code at runtime to handle this new type. And I'm going to update this function in the JIT emitted page. So right here, we're calling blah first with a string, and then we're calling it with an array. And for each time that happens with a different type, that code at runtime in the JIT page is going to be updated. So here's a good illustration of that. First, you call this function foo. It handles bool by default. But then you call it with the number 23. Now it handles integers. Then you call it with a string. Now it handles string. Right? The inline cache is what makes this possible. Frequent writes to the JIT emitted code during runtime.
Yep, and it's actually overriding code as it's receiving new types.
So I mentioned, I might have mentioned some of these. There's fast paths and JagerMonkey. And fast paths are operations where they have been completely JITted. There's nothing but JITted native code to handle the operation. That's a fast path. And then there's slow paths. Slow paths are encountered when, for example, the inline cache, when a type isn't known. When a type isn't known, a slow path has to be taken back into the interpreter to look up the type to be able to generate the new JIT code. So that's what a slow path is. And then there's stub calls. Stub calls are defined as when JIT code has to call into an existing C++ function in some library that was shipped to you in the browser. And that's typically done for when fast paths haven't been fully implemented yet, or they're there to help augment a fast path and do some operation that's not easily done through JIT emitted code. The memory allocation classes of JagerMonkey are not quite as interesting as TraceMonkey. There's first the executable allocator class, which handles calling the low-level APIs like virtualalloc on Win32 or mmap on POSIX platforms. And they all allocate, again, their code readable, writable, and executable. And that's really necessary to support the feature of the inline cache. And we'll definitely talk about that in detail in a little while. And then there's the executable pool class. And what that class does is it takes these larger JIT page allocations and it breaks them up into smaller pools. And anytime other components of the JagerMonkey engine want to write code to memory, they ask this class, hey, what's the best size pool you've got for this chunk of code that I've got to write to memory?
Okay, so we've also looked at LLVM, and LLVM, it's much bigger than a regular JIT. It's a set of libraries. It's a kind of overarching project that's trying to implement pretty much everything that you can use for compilation. That includes an instruction set definition, just a document that explains a kind of very generic instruction set that you can emit or you can work on as an optimizer. LLVM produces a suite of libraries that's used for everything from parsing code to optimizing code. Optimizing is how the project got its start, as Chris Latner's thesis, like in the early 2000s. And it also obviously includes a JIT engine, it includes a linker, and it kind of does everything that you might want to do with compilation. Before it had a very standard conforming front end, it used GCC. So it took GCC to parse C, C++, or anything else that GCC handles, and fed it into LLVM for optimizations. Now kind of it blew up to where there's a lot of dynamic languages that are trying to optimize use LLVM's backend, since it kind of implements everything you might need once you already have your language definition. There's Python implementations, there's lots of Ruby implementations. The Glasgow Haskell compiler uses it as its default backend. There's a PHP, there's pretty much implementation for almost any language that you might want to emit. So this is why we kind of looked at it, since it's getting more and more prevalent, and we've noticed that it's going to get even more probably in the future. So here's like a kind of a very generic, very high-level overview of what happens inside the framework. You have a collection of source files. It doesn't have to be C, but it happens to be C in our example. That gets fed into Clang, which is the LLVM's project, C, Objective-C, and C++ compiler, which which I think the iDevices and OS X now support. LLVM is now being mostly sponsored by Apple, so you'll see a lot of Apple's stuff moving to LLVM. Clang produces LLVM's intermediate representation, which gets fed into one or more optimizers. And there's lots of built-in optimizers and lots of optimization strategies. And then once you have your optimized IR, they can potentially be lowered to a DAG, which is referred to, and then that can either be stored as an object file. You can feed it to a linker so it can create a normal binary, or you can feed it to an execution engine, which is what we were more interested about. And then the execution engine will use a platform-dependent component and emit native instructions. And yeah, we're worried about the JIT. And right now, I think the most supported platforms are x86, obviously, and ARM. So yeah, let's say I have a project, like I'm implementing my own toy language, and I want it to be either performant or I want to emit code. That's usually the point where we find a lot of projects pick up LLVM's libraries and start using LLVM. So, and as we were looking at LLVM, we realized that it's not really as straightforward as just like linking to LLVM.so and starting emit code. There's a few different strategies you can take to start to connect to LLVM. The most kind of obvious way is just emit IR directly. You don't have to write bitcode or anything. You could just use their API to build your own instructions to emit the code you're using as an LLVM native instruction set, and feed it to the rest of the system, and it's going to be compiled, linked, and everything. And MacRuby takes this approach. MacRuby sets up Objective-C bridge to Ruby and kind of backends into LLVM natively. JIT is also using it as a backend now. It's a default backend now, but I mean, if you already have a fairly mature project that has its own VM instruction set, it has its own VM interpreter, and you kind of took the time to implement everything on your own, there's really no reason to throw that away. Plus, if you're distributing copies of your software, you might have some cases where you just can't bundle LLVM with it. So a popular strategy that we've been seeing is you have the front end does the same as you would without LLVM. You would create your own instruction set, your own bytecode that you've implemented for your project, and then once you've emitted all of your code base, you can have a visitor that slowly kind of walks each of your instructions, converting it to LLVM equivalents, kind of build up a module. And once that kind of translation has been done, that will feed it into the LLVM framework and feed it to the execution engine. Rubinius takes this approach since Rubinius had its own VM before, and they have their own bytecode. So if you run a Ruby file with Rubinius, it's going to spit out an RBC file or an RBO file, and that will have Rubinius bytecode. So then once you load Rubinius bytecode and you have LLVM support enabled, it will translate Rubini's bytecode into LLVM bitcode and start executing. And ClamAV, the open source virus scanner, has a way that you can implement your own scanning code, and it's done in a subset of C, and that subset will use LLVM's front end to compile it to bytecode so that you can make your virus engine support more formats. So I mentioned module. A module is the closest analog to a module is a translation unit. So like everything that you might need to emit code or to run code gets attributed to a module. That would include instructions, that would include all your constants, that would include your data, and pretty much anything that you need, anything that you would need to emit code goes into a module. Then you create an execution engine object, which receives a handle to a module. An execution engine is the interface that kind of handles everything to do with JIT emission. And then nothing happens after that, right? It doesn't just emit everything as soon as it sees it. Once as a client, as the kind of as the client program for LLVM requests a handle to a function, which is probably going to be main initially or some equivalent of main, only then we'll actually start generating. Only then we'll actually start trying to emit functions. Then only emit what you asked to emit. Like it's not going to follow all calls. It's just going to fill with stubs and kind of stop there. And then, and then you're running. And then once you've received a handle once you receive the handle to a function, you just get a function pointer to like a native function that you could just call as if it was an any C function. And here's a kind of another high-level diagram of the JIT class and its auxiliary classes. You'd have the execution engine interface, which is implemented by the JIT class, which right now there's only one JIT class, but the project's working on an MC JIT class, which is going to be another execution engine, which tries to be a lot closer to hardware and tries to be a lot more knowledgeable about the assembly you're emitting. And that connects to a JIT code emitter, which handles a lot of your IR passes, and your JIT memory manager, which is as we'll get to later, we feel it's an important class that handles all the memory you're emitting to. So it allocates your readable, writable, and executable pages. It has callbacks for pre-emission and post-emission, and it pretty much does anything that would require memory usage. And then all of that is totally platform independent, and the only platform dependent part is like in this x86 JIT info class. Well, in this case, x86 JIT, since it can be any platform. And then that will handle all the machine-specific passes that will actually emit your native code.
And if you're looking to use the LLVM framework in your project and you want to implement the protections we're going to go over, like Jan said, the JIT memory manager is the class that it needs to be done in. Mm-hmm. It's very important. So this brings us to the reason why we're all here, right? JITs and application security. How do JIT engines affect the security of the applications that use them? Compiling code is traditionally done by developers, not you, right? It's done by some guy who has some code on his desktop, and it's his code, and he knows who wrote it, and he compiles it. And no one cares if his compiler crashes, because it doesn't affect you, it doesn't affect your data. But now that code compilation is happening in your browser or in your language runtime. So that's a trust boundary we feel has kind of been crossed there. Because you're now compiling my untrusted code that I've sent to you over the internet. One of the major things that can go wrong with JIT engines is incorrect code emission. And this is something that we feel that no one is really talking about. JIT engines can't always produce perfect code, right? It's impossible, for the same reason that GCC can't produce perfect code and Visual C++ can't produce perfect code. So compiler bugs are usually caught when someone is developing code, testing an app, and it's all done on the development machine, and then you just get the fixed final product. But what happens when those bugs happen in your browser? Here's a great example of what can happen. This was just patched in June in the x64 JIT of the JVM. What they intended to JIT, the code they intended to JIT, basically took a value from the top of the stack and added this constant to it, and then popped some values out into R flags. What the JIT actually emitted was this instruction that shifted the stack pointer by this large constant in memory and then did the same operation. And this was, of course, just marked, oh, this is just a stability bug, it crashed. It's not just a stability bug, and these types of problems can lead to security issues. And as long as we're marking them stability bugs, no one's going to take them seriously as the security bugs they really are. And there's plenty of examples of this. Another example, in the beta version of Firefox 4.0 from earlier this year, someone reported a bug where they were surfing Gmail and the JavaScript in Gmail crashed their browser. And I looked into the bug case and I saw what was really happening there. Basically, there was an inline cache still in place. There was still native code in place for operating on an object that had already been garbage collected. And that's sort of a classic use after free situation, except for the fact that the JIT emitted x86 that jumped into a random spot in memory. That's awful. If you can get code at where it jumped to in memory, then you can control the flow of execution. Another great example of this is a bug reported earlier this year, and to their credit, Microsoft marked as a security issue, was the CLR JIT confused the state of an object as either being null or non-null, depending on its properties. And what could happen there could be some authentication bypasses or authorization bypasses when the higher level code goes to check the state of the object. The JIT produced incorrect code for checking it. And this is a great example of a bug that you can't easily fuzz for, or you can't easily see in a disassembly. There'll be no crash as a result of it. So what usually triggers these kind of bugs? In the case of the Mozilla bug, the use after free is what happened. Of course, integer-related bugs can certainly come into play here when you're calculating, where you're writing code to memory and where other code is stored and branching to that other code. It's a lot to keep track of. And then the most interesting case is incorrect logic, is when you have all these complex JIT components and just one of them is out of sync with the others. And the next thing you know, you're generating code that does things you didn't intend it to do. And this really raises the question, is this a new vulnerability class? Well, it really depends on the root cause, right? In the case of Mozilla, it was use after free, so we know the cause of that. But if I can find some way of fooling the logic that your JIT engine uses into producing code that doesn't do what the JIT engine intended it to do, well, we feel that no one has really kind of debated that yet. And there really needs to be a discussion about it in the security research community to understand more about these bugs and understand how they can be triggered and how they can be exploited.
And just another I feel interesting difference between having a JIT and having a traditional compiler is if you're compiling code that's not to spec and the compiler burns your house down or does something awful, it's okay because you're feeding it code that's not up to spec, so it's not really up to the compiler's author what happens since you're not using it correctly. But a compiler sitting on the user side can't just reason whether or not something is spec or not spec. It has to kind of fail gracefully for all inputs, regardless of whether they're conforming to the language spec or not. Okay, so incorrect code emission is a bug that's inherently in a JIT engine. But the JIT engines also create an environment which makes traditional bugs a lot either more exploitable or just a lot more dangerous.
Yeah, they introduce all these properties into the application you use them with that normally just wouldn't be there through the use of other libraries. And things like native code emission are an obvious one. Some exploitation primitives that they introduce is a JIT spray. JIT spray was written about and spoken about by Dion last year. Which we'll get to in a little bit. Also, you're emitting you're allocating and using readable, writable, and executable pages, which goes against a lot of modern operating system policy. And there's also some ROP implications, which we're going to discuss also. Yep. So the JIT spray was targeted initially at Flash's ActionScript JIT, and the technique kind of exploited the notion that x86 instructions aren't aligned, and you could have x86 instructions kind of sitting anywhere in code. That if you embed constants as immediates in instructions, they're going to be directly if they're optimized, you're going to be straight in the code you're emitting. So the kind of basic idea of a JIT spray is you create a lot of code that uses a lot of constants, and the constants contain your shellcode. So then if you can change instruction pointer and jump somewhere in the middle of your constant, you can have valid x86 instructions emitted in your final instruction stream, which can be joined together by semantic knops with the pieces left over from previous instructions. So we took a stab at implementing JIT spray in other JIT engines. And we kind of came to the realization that it really depends on the type of JIT engine. For example, JagerMonkey does not produce very highly optimized code, and that's by design, right? It's not meant to emit optimized code. It's meant to emit native code as fast as possible for whatever JavaScript it's been given. So trying to do JIT spray on this is very, very difficult, as you can see. In this case, we created a new array with a bunch of constants, and you can see we get our constants into memory. But the problem is that there's all these other bytes surrounding those constants, so it's really hard to do like a stage 1 shellcode out of that. Even if I can jump in the middle of one of my constants and get some instructions I want to execute, there's a bunch of bytes in between that and the next constant that I can't control that will mess up my execution of my shellcode. And as you can see, I mentioned it's not optimized. You see here the function, it calls into a C++ stub. It calls a new init array. And then what it does is it loads the return value into the EDI register. And if you keep looking down through the constants, you'll see that it keeps reloading that pointer over and over again, even though it doesn't need to. So it's just one example of how unoptimized the code that the JIT is emitting really is. But if we look at TraceMonkey, for example, TraceMonkey emits highly optimized code because it gets compiled down to a lower level IR that's closer to the machine instructions. So we played some games here with floating point, for example. And floating point on 32-bit platforms, floating point number will occupy 64 bits of memory. So we take a floating point number that represents a bunch of x86 NOP instructions, and we just assign it to a bunch of variables. And by doing that, we get a bunch of our constants much, much closer in memory, much closer to the original JIT spray attack. albeit with some bytes in between, but those are predictable and they're much, much smaller. And you can actually get a stage 1 shellcode out of this through the TraceMonkey engine.
So I think one of the main side effects of JIT engines is that they always need, for the most part, writable and executable memory. So this weakens depth quite a bit. This breaks assumptions behind mirror pages, which kind of try to separate the stuff you're writing to the stuff you're executing. So you'll have two mappings to the same kind of memory, one marked readable, one marked writable, and one marked executable. So you write to one place and you execute from the other place. In the case of a JIT engine, this can give rise to blind execution, whereas traditionally with mirror pages in place, you need to know both the place where you need to write and where you need to execute from. Whereas here, you really don't need to know where to execute from. Since if you're writing to the JIT page, you already kind of emitted code. You know the code you're emitting. And all the function calls are already stubs into the stuff you're writing. So all you need to, so if you potentially spray your code into a JIT page, then all you need to do is just call that function that you already had a handle to, and that already is going to point into your potentially your shellcode. And one protection against this is, emit code and then remove the write permission. But this really isn't going away for inline cache designs. It's curious.
Yeah, so like we said, inline cache designs have to rewrite code in memory constantly. That's how they're designed. So again, if you don't handle integer type, you have to update the code in memory to handle a string type. That's going to happen pretty frequently enough that making a trip back through the kernel and making a context switch to mark the page only readable every time that happens is just too much of a performance hit for an engine that's designed to make a browser a lot faster. So the RWX page problem isn't going away anytime soon for JITs with an inline cache design. It goes against the reason that they exist. So readable, writable, and executable pages can obviously be repurposed for a number of different things. Say, for example, you have an array and you have an arbitrary index out of that array, and that's the vulnerability. One thing you could do if you can read from that is you point the index into one of the JIT pages that are mapped, and you read some bytes out of it. Well, you won't just get a bunch of native code that's been written out. You'll get branches back to the DLL that wrote it there. So you'll get addresses that will tell you where the DLL that emitted the code is in memory. And that can be used to defeat things like address space layout randomization. Another thing you can do if you have an arbitrary write is move the index over one of those JIT pages, overwrite some code that was JITted there, and then trigger the original code, the original high-level script that was JITted to that location, and that's blind execution. You don't have to know where that code is in memory. You just have to trigger the original code that was JITted there, and you get that code execution for free. And another one that we think really hasn't been touched on is adjacent pages with permissions that allow for this to be easily abused. So here in Firefox 5.0, we have an example. We have one page that's mapped readable and writable, and then just adjacent to that page is an RWX JIT page. There's no gap between those two pages. So what happens when there's a heap overflow in that readable and writable page? You just keep writing code onto the executable page, trigger the JavaScript or the high-level language that was JITted there, and you get code execution, again, for free. You don't have to know where that code is. Another way we can use these is in a traditional ROP payload, your first stage one is going to be used to call into something like virtual alloc or mmap and allocate a bunch of executable memory. So you have to find a stub in the DLL that you're ROPing off of to do that. And if that doesn't exist, well, you already have all this readable, writable, executable in memory. You just spray a bunch of it by abusing the JIT engine, and then you just use your stage one ROP payload off another DLL, write your stage two into it, and execute it.
So, speaking of ROP, ROP gadgets are small pieces of code that you can borrow from already executable and already mapped pages to kind of bounce across and start loading your second stage shellcode into. But this, for the most part, needs for predictable addresses and in already loaded pages that have been loaded as the process is running. But the JIT engine can already be spraying lots of code that's predictable, so you could just ROP off the code you just sprayed, And we'll get to randomization and placement in a bit, but for the most part, you could have predictable offsets into gadget pages, and you can even kind of make your own gadgets in the JIT pages, which we're referring to as gadgets with a JIT. Yeah, and it's pretty much unconstrained to how much native code you can produce, so you're not limited to just the stuff that's been loaded.
Yeah, I mean, that's one big constraint with the ROP technique, right? ROP was invented to defeat DEP. It was invented to defeat data execution prevention, not address-based layout randomization, which means even if you have a bunch of usable ROP gadgets and a single DLL in memory, you don't know where that DLL is. In the case of a JIT engine, the JIT engine produces lots and lots of native code on lots and lots of different mappings. You don't need that one single instance in memory.
Yep, and then the JIT engine will probably not use the OS's loader, or so there's no, like an ASLR policy will not explicitly apply to a JIT engine.
Not always, as we'll get into. And one thing to note here is that this is not really the original JIT spray attack, so it doesn't require that you can control a bunch of constants in memory. So the protection mechanisms that are in place now to defeat JIT spray will still fall over against this. So finding usable ROP gadgets in your JIT emitted code pages really depends on the JIT design. If the code is highly optimized, sometimes it actually be harder to find gadgets because there's less code to look in. The code is just, it's tighter. And it depends on how the emitted code transfers execution, right? Either it just jumps all over the place. Does it use like a return base? Does it return all the way back into the C++ code and then back into the next emitted stub? Or is it just frequent calls to C++ stubs? It really depends on what that emitted code looks like. But the main takeaway here is what input can I feed this JIT that will produce some segments, some emitted native code that will contain a usable gadget. And finding these requires a lot of time and effort into what source code will produce, what source code can be fed to the JIT engine that will produce what usable native code. And then in addition to that, we kind of found you need a specific tool for finding these in JIT emitted pages because all of the existing ROP payload generating tools operate on DLLs in memory or a DLL on disk, and that just sort of didn't fit what we wanted to look for.
So another technique we've been looking at, which we termed JIT feng shui, inspired by Alex Sotorov's research in 2007 on JavaScript heap feng shui. And the premise of the heap feng shui attack was the fact that the JavaScript heap is deterministic. You can make various allocations to kind of groom the heap to be more predictable and to better reason about where your shellcode will be. We kind of borrowed the similar technique, whereas you can, since the code is provided by the attacker, you have complete, and the JIT is completely deterministic. You can also predict where you can also predict where and how your code's going to be emitted.
So here's a quick example of like the JIT feng shui technique and feeding the JIT engine a specific input to get a usable ROP gadget out of it. In TraceMonkey, we found a bunch of gadgets like this where it pops a bunch of values off the stack, which you control in a ROP payload, and then just returns. Right? We found this to be kind of usable because now we can call other sorts of gadgets that call values in those registers instead of calling other individual gadgets that control those registers. We can all do it in this single gadget.
And the other implication here is LLVM bitcode can be used as an intermediate format. Like Google's Portable Native Client project is attempting to extend native client to be cross-platform. So you're delivering your binaries in LLVM bitcode format, and then those get executed in the sandbox in the client. But if you can exploit the engine and point the bitcode pointer to a different place, or inject your own bitcode, and then point the JIT engine to start emitting that, then you can potentially have totally cross-platform bitcode. Cross-platform shellcode.
So combining these two, JIT feng shui and gadgets, it basically means you control all the inputs, you know exactly what inputs are going to produce what JIT emitted code that contains gadgets that you can use. But there's a few interesting things about this. It does circumvent the protection mechanism that was put in place to stop JIT spray. And we'll get to what that protection mechanism is. But it's also really easily defeated by some other simple protection mechanisms like random not padding and allocation restrictions, which we'll be getting to. And then again, also, it's difficult. it's really difficult to pull off because you have to do a spray attack, right? You have to allocate tons and tons of memory to make it work. And of course, we only researched it on Firefox and LLVM so far. There's lots and lots of other JIT engines that need to be looked at to see how controllable their outputs are and whether those outputs contain usable gadgets that you can find at predictable offsets in the JIT emitted page. So actually, the whole time we've been talking about attacking JIT engines. Now we're going to kind of transition into how you can defend JIT engines. There's a couple of different techniques you can use, and a few of these are provided by the operating system already, like ASLR, address space layout randomization, which basically takes all the things that are in memory and shuffles them around so you don't know where they are. And then there's data execution prevention, which says that don't treat data as code, right? Don't allow the attacker to execute data as valid x86 or valid whatever instructions.
So code signing is it's a feature of some modern operating systems. The iOS and iDevices is a prime example, which verifies that all code that is allowed to run in the system is verified by some party that this is trusted and that we can execute this. So if you were to inject your own code, it will not. The signing will fail, and the OS will refuse to run it. JITs negate that by design. Like you're always emitting native code, and you're not kind of executing what was on disk earlier. And so much so that the performance benefit of the JIT engines in mobile Safari and iOS is causing Apple to remove code signing on mobile Safari. So because of the JIT presence in mobile Safari, code signing is being turned off for mobile Safari. And so JIT engines, we've been discussing that they have no control over their input since source can be completely attacker provided. But they have complete control over what they're emitting and where they're emitting it. So that can introduce a lot of ways to protect themselves.
All the code a JIT engine is emitting is, by nature going to be position independent. So where it's placed on those JIT pages is completely up to the JIT engine, and that gives it a lot of flexibility in protecting itself.
So in terms of randomization, on OS X and Linux, if you allocate memory with mmap, that's going to be randomized by default. On Windows, it's not so, but you can ask for a specific address to be allocated. So you can implement ASLR on your own, and this will kind of bring you up to an operating system's level of randomization. V8 and i9 both kind of specify random address to have their memory loaded at.
Yeah, if you call virtual alloc a number of times, you're going to get back a bunch of contiguous page allocations, and that's really bad in the case of readable, writable, and executable memory, because now there's a giant block of it with no gaps in between.
Okay, so here's just a really crude approximation of what an address looks like, and here white means it's predictable, it's unrandomized. So we have so first, let's say we do introduce allocation randomization to memory we're asking. So we're pretty much randomizing all but the bottom 10 bits. And that will bring us up to the randomization that's offered by an operating system. But we don't have to stop there. You're emitting code into that page, so you can technically emit anywhere you want. So one thing you can do is pad each function by a random amount of nops. These bits of entropy are fairly approximate, so if you're emitting anywhere from 0 to 7 nops before you start emitting a function, that will make your bottom three bits totally unpredictable. But again, you still have about 6 or 7 bits in the middle that are totally predictable. But if you have a JIT engine, you generally see all the source you're going to be emitting right away. So as we mentioned earlier, the Lexer, the parser, that happens way before the JIT engine gets a hold of your IR. So you already know about how much code you're going to be emitting, and you know about how many code blocks and functions you're going to be emitting. So nothing is really stopping you from shuffling them before emitting them. So function shuffling can also extend the high of those low 10 bits to provide an address that's almost completely unpredictable.
Earlier we mentioned the case of adjacent pages where the first one is writable and readable, and the second one is readable, writable, and executable. This can be easily fixed in the case of just a straight up linear heap overflow from that first page into the executable page by using a guard page. And the way the guard page will be implemented is you just allocate this memory just beneath the JIT page there in between the regular heap memory and mark it read-only. So anytime a write is attempted on that page, the process would crash or segfault or whatever, or catch a signal. And that's much better, obviously, than an attacker executing code. And this is really important because of the whole blind execution technique. You don't need to know where you overwrote code. You just need to know you overwrote code in a JIT page, and you have some JavaScript that was JITted there, and then you call it.
It's also really simple protection to implement.
And there's pretty much a very, very, very minimal performance impact in using guard pages.
So one of the kind of first protection mechanisms was created for JIT engines is constant folding. This was made to prevent an attack similar to the JIT spray, whereas you're providing a lot of constants with your own code, and you're trying to kind of make it a lot harder to place continuous blocks of code into your emission. Since x86 instructions key are pretty small, having 4-byte blocks is pretty bad. So the solution was to fold large constants into smaller constants and then reassemble them at runtime. So you take any constant that's over 2 bytes long, you break it up into multiple instructions that perform a similar operation with smaller constants, and then you reassemble back later. So that prevents you from inserting larger constants with more code. V8 implemented this initially, but now they use constant blinding, since you can still get a few valid instructions in a space of 2 bytes. Second of all, the instructions that break apart constants and reassemble them later are also predictable. So those can potentially be part of your shellcode. Glad you asked.
So constant blinding, we think, is actually the real solution to the original JIT spray attack, where at runtime you generate this random value, this random cookie. And anytime you come across an untrusted immediate or untrusted constant provided by some JavaScript or some high-level language, you XOR that value by that secret cookie you've generated. And then you emit code that un-XORs that value out at runtime. It's potentially a small performance impact to the process, but there's a huge gain here because the attacker won't be able to get in that stage 1 payload anymore because it'll be XORed by that secret value that the attacker doesn't know. In the case of you just writing a constant in memory and comparing it to something else, there could be a little bit of performance overhead here because you have to use an additional register to then go and get that value back out by doing the XOR operation in reverse. But this is probably the best way at stopping the original JIT spray attack.
And you don't always need to increase your register load. In some cases, you absolutely need to, but in a case like this, where you're just XORing an immediate with a register, you just need to emit an extra instruction. So.
Yep.
So one notable kind of side effect of a JIT spray is you're going to be allocating a whole lot of memory. And if you're in a predictable environment like a browser where you pretty much know what the workload's going to be like, you could just simply prevent allocation of that much memory. This is not that useful in a dynamic language runtime or just a very kind of generic JIT like you'd find in JVM or CLR. But if you're in a browser, you could definitely cap it at a low enough level that you're not allocating into enough addresses.
So yeah, I mean this makes a lot more sense for browsers because for JavaScript, a typical web app doesn't need to allocate a few hundred megs of JIT pages. It just doesn't make a whole lot of sense. We think it can be effective there, but in language runtimes, like Jan was just saying, probably not so much. So here's our comparison chart. We took a look at a number of different JIT engines that are out there. Some we looked at a little bit more in depth than others, and some we basically talked to the developers and the engineers behind it to kind of get some information. But as you can see, a lot of the protection mechanisms we've been talking about really just aren't implemented in a number of JITs. The two that are obviously kind of leading the pack here are V8 in the Chrome browser and IE9. They both implement a number of these protections. Guard pages is very, very recent in Chrome as of just the other day. So that one you'll be seeing very, very soon. And also something worth noting here is after the original JIT spray attack, there was some code committed to the Tamarin project, which shares the NanoJIT engine with Firefox, if you remember from the beginning of the talk. And there's some code in there that emits a bunch of random NOPs in memory. And that code was shared by a Tamarin developer to the Firefox project. But we started looking at the code and we realized that it's not on. It's turned off. So that protection mechanism was never actually in place. So we didn't give them credit for it, but the code is there.
Also, some columns like LLVM and JVM, it might not make a lot of sense to implement these protections for a totally generic JIT engine, which is supposed to handle dynamic languages in general. But we added it to our table for completeness. Yes?
Does having both constant folding and constant winding make sense?
No, probably not.
Probably not. I really don't see any reason to do constant folding. Yeah. I mean, maybe in some higher optimization in your compiler, but that's really not related to security and what.
In terms of constant tax, I think blinding should get you covered.
Yep. There was another thing here. Also, another thing to mention here is that we've actually been talking to the Firefox developers, and a number of these protection mechanisms. I don't know how many or which ones, but some of them will be implemented in a newer version of Firefox in the near future. And some things also don't make sense, we should point out, like guard pages, for example. They don't make sense for IE9 because IE9 produces JIT pages marked as readable and executable only, and that's a byproduct of their JIT design. It wasn't a JIT we really did a deep dive on, so I can't tell you too many more details than that. Hopefully we'll get to that post BlackHat. But yeah, so that even though we have an X there, they don't actually need guard pages because their pages aren't writable.
Okay. So I've been just discussing some of the work we've been doing. Jitter is our toolchain that we've been writing on top of Ragweed and Nerve. Ragweed is you can check out Ragweed at the tool fair later today.
Tool Arsenal.
Ragweed is a scriptable dynamic debugger in Ruby, and Nerve is a hit tracer. And our entire toolchain is built on top of that. Jitter lets you trace JIT code emission. It lets you track various changes in memory protections. It let you instrument what your JIT fuzzer is doing. And there's an independent class searching for that lets you search for gadgets.
Yeah, and all this, like Jan said, all this is implemented as Nerve scripts, which is a tool that exists right now on GitHub. We just sort of used it to create this tool chain. Next slide. So the first release of Jitter basically works against LLVM JIT and the two Firefox JITs. And we chose a bunch of what we think are interesting hook points for tracing those engines. It's hook points that you would normally get if you were running like a debug build of the browser. You would see all this, this output from the JIT engine. But if you're trying to write an exploit or something for one that's actually on somebody's desktop, you're not going to get that version. You're not going to get the debug version. So we went and we just kind of looked at the binary and found all these interesting places to hook. And some of the things that we hook are obviously where it emits native code into memory, where the polymorphic inline caching hits, those types of things. We extract arguments, we extract the different instructions the JIT engine has emitted. And then we also released kind of a generic script. So if you're researching a new JIT engine and you don't know much about it, run our generic script and it'll look for the allocation of executable pages. And then you can sort of use its output to then go and start reversing that JIT engine and looking at its memory allocator and working backwards from there. And then another thing that's built into Jitter is the gadget finder. I said we had to write our own ROP gadget finder. And it is repurposable. You could use it for searching DLLs and things like that on disk. But we did write it to sort of hook into our Jitter toolchain. And as JIT pages are generated, look at their code, analyze it, and store it to do gadget comparisons later.
Yep. And Jitter and the gadget finder are all going to be released within soon.
Yeah, we are going to release it. So fuzzing JIT engines is difficult. We've been discussing before that they're kind of removed from where your input's coming. So a lot of the time you really need to have your test cases need to conform strictly to a grammar for them to even get to the JIT. We wrote a few fuzzers. We wrote a Rubinius fuzzer that generated permutations of Ruby grammar. We created a JavaScript grammar fuzzer as well for targeting Firefox. And we created a fuzzer driver framework, which kind of did crash binning and all the process management and test case feeding. The Rubinius fuzzer was the easiest way to reach the LLVM JIT from a higher level language.
And just a side note, so we've been looking at LLVM directly, and LLVM, one of its valid inputs is you can provide a bitcode directly. So we're like, hey, let's, it's a binary format, let's just dump fuzz it before getting into any more detailed fuzzing coverage. But what we quickly noticed is that we were getting way too many core dumps for this to be useful. The bitcode reader class and the bitcode reader in general LLVM is totally not designed to be a trust boundary or designed with security in mind. It is a performance kind of first and only, performance is its first and only goal. So I guess performance and correctness. We found a bug that let you reset the bitcode reader to any point in memory and instantiate bitcode from anywhere. We submitted a patch. The patch was accepted, but the feedback we received was, well, we're not really treating bitcode as a security boundary. We're providing a library. If you want to, if you treat it as a security boundary, it's up to you to kind of to validate. But yeah, so we definitely feel it's a security boundary, but it's not up to the LLVM's project.
There's certainly, you can make the argument for the case of someone accepting, like we said earlier, untrusted LLVM bitcode and just kind of shoving it into the LLVM engine to do its thing. And in that case, they're going to find a lot of really fun bugs to exploit.
And the comparison here is to like an OS loader. Like you really wouldn't want an operating system loader to load a binary and then have the binary take over. The first and the simpler fuzzer we wrote a Ruby fuzzer for targeting Rubinius. The Ruby fuzzer actually created valid Ruby code. We could have targeted Rubinius's instruction set directly in its binary format, but that would only limit us to targeting Rubinius. Whereas if we write a Ruby generator, we can target any Ruby implementation, including Rubinius, MacRuby, JRuby, Matz's MRI, and pretty much anything. And the driver that we've alluded to earlier is also written in Ruby. The thing to note is the fuzzer itself was not running inside our target. It was running separate since we didn't want to step on state while we're fuzzing. Just a brief overview of internals. If you're looking at grammar in general, kind of grammar has this, if you're modeling a language, it kind of has this understanding of a terminal and a non-terminal. A non-terminal can be any expression or anything that can generate more than one expression. A terminal is stuff like identifiers, like values, and like any of that stuff. So we modeled terminals as arrays that are permuted, and we modeled non-terminals as Ruby generators that permuted every generator under itself. And just walking and permuting the entire Ruby grammar, every permutation of Ruby grammar would really not get us much good. So the fuzzer was seeded with very common Ruby idioms, just like block definitions, class definitions, assignments, reassignments, and stuff like that.
So we also wrote a JavaScript fuzzer. We looked at all the different browser bugs that are being reported today, and a majority of them are really like they're DOM-related bugs, right? They're use after free bugs in DOM parsing code. You have some element on the page, and you mess with it, and it gets garbage collected, and then you call some method off of it, and you get arbitrary code execution. What we're mostly interested in is bugs in the JavaScript interpreter itself and the JIT itself. So the way our fuzzer works is we took the Mozilla command line version of SpiderMonkey and fuzzed it that way. So we're able to get a lot more test cases in. And what we did was we took the ECMA script spec, defined it in a bunch of text files, and then took those text files, pulled them into Ruby, created some open struct objects, and then iterated over them, calling the grammar in various different ways. And the way that we kind of looked at how we can get to the JIT as fast as possible is we went and we looked at all of like JagerMonkey's fast paths, for example, and we said, let's go backwards and say which SpiderMonkey bytecode instructions reach these fast paths. And then what high-level JavaScript constructs will generate these SpiderMonkey bytecodes. So that's how we reach those JIT functions in our fuzzer. And we went through hundreds of millions of iterations, and we did find...
Over a few months?
Yeah, over about 2 months. And we did find some interesting things. We did find one critical bug that we reported. It was actually in the SpiderMonkey engine, not in the JIT, but it was a really cool bug where you create a new array, you set the length property on the array to max unsigned int minus a few on 32-bit x86. And you'd think that would grow the array to that size, but it doesn't. It's just a property. It just stores that value. And then you set up a callback function for the reduce write method. And then you call the reduce write method off that array. And what happens is that reduce write callback is going to get called for every element in the array. And unfortunately, they used a signed integer where they should have used an unsigned integer. And you basically got an arbitrary index outside of this C++ array that backs that JavaScript object. And the cool thing about this bug was that in that function callback right there, you could either read from that current argument and get just an arbitrary info leak from hundreds of thousands of different spots in memory, or you could get arbitrary code execution by just calling a method off of that current argument. So this was a really, really cool bug that we kind of played with and using the JIT to exploit because the pages were readable, writable, and executable. So we consider our fuzzer a success for this bug alone.
All right, so we'd like to finish up with just something we've been looking at, which we haven't really had the time to do yet, but we think it's going to be really beneficial in the future for finding information leaks. So as more stuff gets randomized, we feel that information leaks are going to become much more valuable as bugs. And fuzzing for information leaks is a little more difficult than just fuzzing for memory corruption. Because if you're getting memory corruption, then your process will crash, and that's really noticeable. And binning crashes is really easy. Whereas leaking information, you'll just have a slightly different behavior, but your process might not crash if you're just kind of reading out of bounds data accidentally. Sure, I mean you can instrument it with something simple, something like Valgrind or another memory tool. But that slows you down quite a bit. Just running something inside Valgrind or another tool that will watch for memory writes, it's going to be really not prone to fuzzing since it's going to be extremely slow.
Yeah, there's no way we could have done the several hundred million iterations we did through our fuzzer had we used something like Valgrind to watch for out of bounds reads and writes.
Yep. So one of the ways that we're looking at and we think is really useful in the future is differential fuzzing. So the idea is you have two or more implementations of the same language spec, and you're generating your cases according to that spec, and you're feeding to both engines concurrently each individual test case. And you're really kind of targeting your test cases to have side effects, to produce data, to iterate through structures, or to kind of do stuff versus just modifying properties. And as you have each run, you're looking for differences in those side effects. So you're looking for different permutation orders, you're looking for different object representation, and you're just looking for stuff that differs between two implementations, but doesn't necessarily crash the process or cause concern. And once you spot differences, some engines can have different ways of converting objects to string or something, so you can account for that in your fuzzer. But if you're looking for differences that you're not aware of, that can actually be a leak from the internal state of the language implementation. And we just think it's going to, so a clear example is you can use D8 and JS, which are the command line versions of V8 and Mozilla's JavaScript engine. And any differences can potentially lead to an information leak.
Yes, so you just feed them both the same test case, record the outputs, and then compare those outputs. And if one engine outputs a string type and the other outputs an integer type, maybe something went wrong there, because one of them is according to spec and the other one isn't, and you want to find out why the other one isn't. Is it leaking something that it shouldn't, or is it just some benign case where it just doesn't follow the spec?
Yep. And we found a few papers from academia that discuss differential fuzzing for finding errors, but we haven't really seen much research in the security community. And with that, anyone have any questions? Yes. Just so writing the JIT engine fuzzer took probably a week and a half to 2 weeks because it's really simple, right? And just went through the documentation for the JavaScript ECMA spec and then just wrote it out to text files and parsed it. And adding new rounds for the fuzzer takes a couple of minutes. So I definitely think development time was worth it. And we have a few other things to report as well. Mm-hmm. And new rounds have been added, like as we're doing other things, you just, fuzzer finished running, let's add more test cases, more rounds.
Any other questions? All right, cool. Well,
yes.
Oh, okay,
sorry.
Yes, we have a question. So the question was, in the future, are we going to look at other JIT engines like Dalvik on Android. Absolutely. We had Dalvik as an original target, and then we realized that maybe this is a little too much work, and we'll save that for version 2 of the talk. But absolutely, certainly, there's JIT engines on your phone now too, and that's a very attractive target to look at.
And LLVM is also used on iDevices and on Android for their graphics pipeline, and for OS X as well. So it's used there too.
All right, no other questions. Thanks for coming to our talk.
Yeah, thanks.